Welcome to this explainer, where we are diving headfirst into a truly mind-bending thesis about the radical evolution of artificial intelligence. Today, we're unpacking Ming-Chen Jugas's fascinating vision for the near future, titled The Neural Computer, A New Machine Form is Emerging.
Right off the bat, I want you to ask yourself a fundamental question. What if AI became the computer itself? Think about it. We are so completely used to thinking of a computer as this dumb box of hardware, and AI is just a really smart app running inside of it. But what happens when that boundary completely dissolves? What if the brain and the box literally become one and the same?
Ming-Chen Juga puts this perfectly. He says, we are starting to expect the machine itself to learn how to run. Just let that sink in for a second. We are moving so rapidly beyond an era where AI merely uses tools on our behalf. We're actually heading toward a new computational reality where the AI physically becomes the computer, managing its own resources, its own logic, the whole shebang.
So, let's jump into Section 1, a completely new form of machine. There are three massive, converging shifts crashing together right now that are basically forcing a total rethink of our hardware. First, agents are mastering real work. Tools like Cursor and OpenClaw, they've moved from fun little experiments to everyday productivity engines. Second, world models are successfully simulating totally dynamic environments. Think about Waymo's self-driving simulations or DeepMind predicting future video frames. And third, our conventional computers are hitting severe structural friction. Traditional software is just so rigid and rule-based, it genuinely struggles to keep up with the open-ended, continuous, natural language tasks of the modern AI age.
Because of all that friction, the entire human-machine relationship is about to flatten out. Today, we live in the agent era, right? You give an instruction to an AI agent, and that agent operates traditional computer software for you, like a smart assistant typing on a keyboard on your behalf. But in the neural computer era, that external software middleman is just gone, removed entirely. You interact directly with a neural brain that has internalized the whole operating system.
Which brings us to Section 2, Defining the Neural Computer. To truly grasp how wild this is, we have to redefine the concept of a runtime. In a neural computer, you aren't installing traditional software packages like Microsoft Word or Photoshop. Instead, you're installing raw capabilities directly into a neural runtime. It's honestly a lot more like teaching a human a brand new skill, rather than handing them a calculator. The runtime is the core identity of the machine. It absorbs your inputs not just as data logs in a folder somewhere, but as fundamental updates to how the machine itself functions and thinks.
You can actually see a really clear evolution here in how systems are organized. Conventional computers organize around explicit, rigid programs. Agentic AI organizes around completing specific tasks using external toolchains. World models organize around predicting environments. But a neural computer, it's an entirely different beast. Its source of truth isn't some external workflow or a hard-coded line of Python. Its source of truth is the capabilities embedded deeply inside its own continuous, living runtime.
Now, for a machine to actually qualify as a completely neural computer, it has to satisfy four really strict conditions simultaneously. First, Turing complete, meaning it can stably hold and execute complex logic without completely breaking down as its memory grows. Second, universally programmable. You have to be able to install and reuse routines just like you would an app on your phone. Third, behavior consistent. Using it shouldn't just randomly mutate its personality, the drift has to be controllable. And finally, machine-native semantics. It shouldn't just be an AI pretending to be a Windows desktop, it needs to form its own native, natural way of being programmed through continuous interaction.
Let's look at where we are right now. Section 3, the first prototypes.
This early prototype phase is basically framed as an imitation game. Researchers are actually using advanced video generation models to mimic computer terminals. And you might be wondering, why video models? Well, because a computer monitor is essentially just outputting a continuous stream of images. So these models, which normally generate scenes of people or nature, are explicitly tasked with predicting what a computer interface should look like frame by frame.
And the results are genuinely wild. By feeding the model just 1,100 hours of noisy terminal data, which by the way is practically nothing in the AI world, it actually learned to perfectly render the appearance and rhythm of a command line interface. It independently mastered shifting colors, syntax highlighting, the exact blink rate of a cursor, and even the rapid scrolling of package installation logs. At first glance, you literally cannot tell it apart from a real hard-coded terminal.
But reality check, here is where we hit the boundaries of the prototype.
The terminal execution logic holds up beautifully. If the AI types a basic command like PWD, the simulated screen updates exactly as it should. But deep symbolic reasoning? That remains a major hurdle. If you ask it to stably compute two-digit math within this neural terminal, it breaks down. It has learned the visual, causal structure of an interface, but it hasn't actually learned the underlying math. Basically, it's painting a really convincing picture of computation, not actually computing.
Moving on to Section 4, Mastering the Interface. Enter GUIWorld. Here, researchers pushed beyond text-based terminals to test full graphical desktop environments. The question shifted from text prediction to, can neural actions genuinely drive a visual interface? Meaning, actual mouse clicks, hovers, and typing inside an operating system like Ubuntu.
To figure this out, researchers injected real keyboard and mouse actions directly into the model's internal architecture. And it worked. They found that something called internal cross-attention, which is basically how the AI connects the action of a physical click with the resulting visual change on the screen, was the absolute best way to teach it page transitions. Interestingly enough, treating the cursor as a visual object on the screen drastically outperformed just feeding the model raw XY coordinate numbers. This proved the model could act as a working memory, successfully managing local, fine-grained interactions on a desktop.
All right, let's bring it all together. Section 5, the future of computing.
Let's contrast the absolute peak AI we expect on our current trajectory, a personalized superagent, with a completely neural computer of tomorrow. A superagent still completely relies on external memory banks, vector stores, and workflows, but a neural computer pulls experience directly into its runtime. Furthermore, the physical hardware substrate is going to change. Instead of just scaling up dense models where every single part fires at once, the neural computer points toward a sparse, addressable substrate. We are talking 10 trillion to 1,000 trillion parameters, where only the exact circuits needed for a task are activated. It's incredibly similar to how the human brain works.
Because of this massive new substrate, the very concept of installation fundamentally shifts. Today, we download libraries, we install rigid software scripts and tools. But in the neural future, you won't just write and compile code. Your human interactions, your demonstrations, and your constraints will actively install capabilities, behaviors, and plug-and-play neural networks directly into the machine's memory. It's a totally different paradigm.
Which leaves us with a final, provocative thought. If the neural computer matures, what actually happens to human programmers? When a program is no longer a block of handwritten code, but a lived capability natively installed into a neural brain, what does coding even look like? The very definition of what a computer is, and exactly how we tell it what to do, is on the verge of changing forever. Thank you so much for joining me on this explainer, and I highly encourage you to keep your eyes on this fascinating shift.